Let's have an example of independent events. To exercise regularly, a survey of 100 students showed that 40% play basketball, 70% jog, and 82% play either basketball or jog. Based on the survey, are playing basketball and jogging independent events? Pause the video and try to see if you'll be able to answer this question. Alright, so let's take note of what we know. The probability that students play basketball is 40% or 0.4, 40, 0.4, 0.40. The probability that the students jog is 0.70. So we want the probability that the basketball and jogging. If this would be the same, if this would be equal, the probability of playing basketball and jogging will be equal to the probability of playing basketball times the probability of jogging, then these two are independent events. Now we know based from this one here that the probability of playing basketball is 0.40 times the probability of jogging is 0.70. Hence we get a probability of 0.28. Now the question is this probability really equal to 0.28? How do we figure that one out? We are also given this one here, the probability that the student plays either basketball or jog. Let's use a different color. So the probability that the student plays basketball or jog is actually equal to 82% or 0.82. Remember, via the general addition rule, the probability that the player, or the student rather, plays basketball or jog will be equal to the probability that the player plays basketball plus the probability that the player jogs minus the probability of the student playing basketball and jogs. So this would mean by manipulation of this equation, the probability of a student playing basketball and jogs as well would be the probability of the student playing basketball plus the probability of the probability that the student jogs minus the probability of the student either play basketball or jog. So we have these values here. We have the probability of playing basketball 0.4 plus the probability of jogging 0.7 minus the probability of playing either or doing either, which is 0.82. Oops, my 28. That is supposed to be 82. And this will give us actually a probability of, this is 0.4 plus 0.7, that would be 1.1. Wait, let's scroll that down a bit. There you go. 1.1 minus 0.82, which would be equal to 0.28. And as you can see, it matches here. So now we can see that the probability of playing basketball and jogging is equal to the probability of playing basketball times the probability of jogging. Hence, we have proven mathematically that the two events are independent. And think about it, whether you play basketball or you jog, it doesn't actually affect the probability of you doing the other activity. Let's have another example. So the probability that a man will live 10 more years is 1/4, and the probability that his wife will have 10 more years is 1/3. Find the probability that A, both will be alive in 10 more years, B, at least one will be alive in 10 years. Pause the video and try to see if you'll be able to answer this problem. Alright, so the probability of a person living usually or ideally does not affect the probability of another person living. So we can say that the probability of the man and his wife living are independent events. So we are asked for letter A, the probability that both will be alive in 10 more years. Probability that both the man and the woman are alive, which would mean that that's simply the probability of M, the man, and the probability of the woman, which by our independent events formula would be the probability of man times the probability of the woman alive. The probability of man being alive is 1/4, while the probability of his wife or the woman being alive is 1/3. So therefore, the probability that both of them will be alive in 10 more years is 1 out of 12, or around 8.33%. Now, what is the probability that at least one of them will be alive in 10 years? So the probability that at least one will be alive. Now take note that this is not just one case that both of them are alive. If at least one is alive, therefore, it's either the man is alive, the woman is alive, or both of them are actually alive. And that's actually 3 cases. So let's list that down. Case 1. It's the probability that the man is alive, but the woman is not. So man is alive and woman or the wife complement. The woman is not alive. The probability the man is alive is 1/4. While the probability that the woman is not alive is 1 minus 1/3, which is 2/3, which is equal to 1/6. Let's write it here. Then case 2 will be the probability that the man is not alive but the woman is alive. So that would be 1 minus 1/4, because that's the complement that the man is alive, times 1/3, which would be equal to 1/4. And last is the probability that both of them are alive, which we already solved here, 1/12. And as we know, if we have different cases, we add them together via the addition rule or the addition principle in the fundamental principle of counting. So therefore, adding all of them, the probability that at least one will be alive would be equal to 1/6 plus 1/4 plus 1/12. And that would be equal to actually 1/2. So there is a 50% chance that at least one of them will be alive, because the other 50% is none of them are alive. Those are examples of independent events.